Thinking in C, Chapter 8a, A First Look at Java. Here's what we're going to cover in our quick tour of Java. First, just a quick word about where it came from, how it differs from C, and then we'll look at a first program. Again, we need to get a feel for how Java programs are different and how you put one together. We'll look at the data types, which are very similar to those in C, fortunately. Control structures, which again are almost identical to C, with an interesting little added feature. And then we'll talk about objects and handles. A handle is a Java version of a pointer to an object. And then finally we'll look at arrays in Java. In around 1990, Sun Microsystems was looking for some interesting things to do and to keep some very bright people very busy. And they were looking into some market opportunities in the world of interactive television. So they put some people together into a team, and they actually moved them off-site and gave them quite a lot of free rein on what they were doing, very forward-thinking type of effort. And as part of what they were doing, they wanted to come up with a new language. It seemed necessary. C and C++ didn't quite do what they wanted to do. And so they developed something that looked an awful lot like C++. And it was originally called Oak. Now remember, this was for TV set-top boxes. This was an embedded type application. And so the language was kind of small and very streamlined for what they wanted to do. It was named Oak because there was an oak tree outside the office of, I believe it was James Gosling, who was pretty much the designer of this language. Well, it turns out that the market didn't quite do what they had expected. The customers that they had lined up changed their mind. And so in about 1994, they decided to change their direction. They just lost their market opportunity, but at the same time, they noticed that the internet seemed to be the obvious way to deploy this new language. And that is how the idea of Java really came about. It was the internet that really gave it the impetus that it needed. The key feature of Java is this idea of write once, run anywhere. In other words, they're really trying to make portability work. And as you'll see, within 3 slides or so, they've done an excellent job. Java is very much like C++. It's based on C, but there are some very key differences. First and foremost, Java is an object-oriented programming language. So much so that everything in Java must reside inside of a class. There's no such thing as a global main program or global variables. Everything has to be within a class. A class is made up of 2 types of things: fields, in other words, data members, and methods, member functions, very similar to C++. There is also no concept of a local static variable, as you can have in C. The only static variables you can have are class variables, and we're not going to talk about those. In C and C++, you have seen how we can separate declaration from definition. For example, in a header file, we'll put the declarations of functions, and then the definition will reside elsewhere. And since C was designed in the day of file-based computing, then that seemed like a natural thing to do, but Java frees the programmer from having to worry about where things go. Pretty much it does. And it takes away the dimension of freedom but responsibility of separating declaration and definition. In other words, everything has to be defined once and for all, fully, within a class definition. If you went through the pointer chapters, you probably saw that there certainly is room in C to make some mistakes with pointers. They're very powerful. They give the programmer what you need in certain instances. But they're also a source of bugs, and so a large class of programming applications like, things that aren't so much embedded applications or things that don't really need hardware access and control. That's a very large class of applications. Well, for them, Java can be a little simpler because you don't worry about the complications of pointers. Another thing that is missing in Java, but it really isn't much of a problem, is a preprocessor. But there is an import facility that allows you to include things defined elsewhere. And actually, it's a little easier to use than in C because there is a convention of where those things are located. So if you follow the conventions that are established with Java, it's very easy to manage a large project and to partition your files into different places on your disk. And it works really quite nicely. Here's our first Java program. As simple as it looks, there's an awful lot going on there, an awful lot that needs to be understood. That's just the way it is. Since Java requires a class to exist in any program, we have to have that scaffolding of a class and the things which naturally go inside of a class. The name of this file is hello.java. You can see the comment there, the double slash is a comment, and that comment ends at the end of the line. The name of the class is also hello, and that is not a coincidence. A file can have at most one public class. You can have other classes, but only one can be public. That's kind of the key class in that file, and it sort of identifies that file's reason for being. And you don't have to have a public class in every file, but it's pretty common. And the name of the file and the name of the class must be identical, including case. So it's got to be a capital H in both your file name and in the class name. Otherwise, they don't match, and you'll get a compile error. The reason for that is, again, I hinted that there is a very nice way that Java gives you to organize your programs, but you must follow the conventions for things to work. And that's one of the conventions. A public class must have the same name as the file, even down to its case. Well, this is a very simple program, but there's a lot of stuff there that you're probably wondering why it needs to be there. This class only has a single function. It's named main, and its whole job is to print out hello world. But notice that I declare main to be public static void. It's public, meaning that it's accessible. It's not a private function. It can be called from anywhere. Static means that this function is a freestanding function. It does not require any particular object to be executed with. It can be just called all by itself. Void is its return type. It returns nothing. And it takes an argument, which is an array of strings. This just has to be the way that you define main whenever you do. The only statement inside my main function is a print statement. System is a class. Out is a particular object of the system class, which gives you output capabilities, and it's hooked to standard output. And println is a function inside of the system class. And so this is going to use the println function, invoking it on the out object, and it passes it the string hello world, and that is what is printed. Well, that seems like an awful lot to have to do and understand just to print out two little words. But again, remember, in Java, everything must be in a class. Now let's take a look at how I built the program, which is in the text at the bottom of the half of the slide. First thing I do is I call javac. That's the Java compile command. And I have to say hello.java. And again, if for some reason that typing of hello does not match exactly what's inside the file for the class definition, you'll get an error. Once that's compiled, it generates a special file called a class file, and I'll illustrate that in the next slide. And it is that class file that is being executed by the next command. The Java command invokes what we call the Java virtual machine. That is a running program. That is the process that executes all other Java programs. And it works. It prints out hello world, and that's the end of that. Let's take a look at exactly what happened in building that program on the previous slide. The source file, hello.java, was compiled by the javac command, and what it did was create a class file, hello.class, which contains an intermediate compiled version of the logic in the first file. Now, I mentioned that you could have multiple classes in a Java source file, and you can. And what you will get when you compile a Java file is you will get a class file for each class. So if I had had 3 different classes defined in hello.java, 2 of them not public, of course, then I would have gotten 3 class files. That class file contains what we call bytecodes. It is not machine code. It is a universally defined format for code, which is called Java bytecode. And it's called bytecode because each internal code takes up a byte. Since it's not an executable file, you can't just run it. That's just the way it is. The only way you can get that to execute is to call upon the Java virtual machine. The Java virtual machine is just a program. It's a program that provides everything you need for a Java program to run. It's the execution environment for Java programs. Since the output inside of the .class file is not executable, you can imagine that Java virtual machine is going to be doing some translation into machine code so that the program can run. And that's a true statement. So it is an interpreted phase. There is some interpretation going on. For that reason, there's a concern for speed. And that's a valid concern. And it's still the reason why C++ is used over Java in many instances. And that, of course, is improving. That is, Java tools are coming out, which are getting better and better all the time. There's even Java native code compilers, which will put out native code, and so they're extremely fast. But the virtual machine is a very important part of the Java philosophy because let's suppose that I'm using the internet and I want to run a program, but the code for that program I don't have. I need to download it. Well, how can I download code from one machine to another and have it run? I can't do that if that code is in native code. And so this intermediate form, this Java bytecode format, is something that can be readily downloaded over a network. And then I will run it in my local Java virtual machine. And that is what gives Java its portability. Because you write code which can run on a Java virtual machine, and then you have a Java virtual machine on whatever platforms you're interested in, and therefore you have true portability. It runs identically from one system to the other. Now, when we were looking at C before, we noticed that there are some differences between the primitive types and the different systems. For example, an int might be 16 bits on one platform and 32 on another, and that can be a problem. And you have to worry about that. Well, with Java, you don't have to do that. As you'll see in just a moment, the built-in types are the same size. And the reason for that is because it is the Java virtual machine that our code runs under. And it's the Java virtual machine's job to make sure that it executes properly on whatever machine it is installed on. The data types in Java are very similar to C++. They come in two categories. One is your primitive data types. We call those built-in data types in C and C++. And objects. Objects being things that you define or that come predefined in the library. And they are made up of primitive types or other objects. The primitive types are practically identical to what you're used to in C, with the major difference that they are of equal size on all platforms. An int is the same size no matter where you go, because it is being translated and interpreted by a Java virtual machine. So you don't have to worry about differences of your platforms. The operators are pretty much identical as well in C and Java, except since there are no explicit pointers in Java, you don't have to worry about pointer operations. And so there's no things like the unary star operator for indirection. There's no ampersand operator for taking an address. And there's no arrow for getting at a member of a structure through a pointer. Casts work in the same way as they do in C. The syntax is the same. They're actually a little safer, though. They actually do runtime checking to make sure that the cast is valid. Now, it turns out that in addition to the primitive types, things like int and long, there are also what we call object wrappers. That is, they are class types. They are true object classes. And they basically allow you to take these built-in types like int and float and double and use them in contexts where objects are required. That does happen from time to time in Java, but we will not see an example here. These are the built-in types in Java. You can see a lot of familiar terms there. There is a Boolean type, Whereas C just uses int for truth values, there's a separate type for logical values in Java. And it can only have two values, naturally, true and false, and those are keywords. The char type, which of course is your character type, in Java is defined to be 16 bits, and it follows the Unicode character set encoding. Now that's a great thing. Remember that in C, they did not specify what it needed to be. Char can be anything that you want it to be on your platform. So whoever writes the compiler and does the library that comes with it, they decide what char is going to be like. And char is very different in different countries because of different encodings. Well, a very nice feature of Java is that it does use Unicode, which is good enough to cover most scripts and languages in the entire civilized world. Do keep in mind, though, that it's 16 bits. It's not small. It's not 8 like it is in C. However, you do have a byte data type, and that allows you to have small integers. They are not characters at all, and it's just a small numeric type. There's also a way of working with byte arrays. There's a lot of support for that in the library. Short is always 16 bits. Int is always 32 bits, and long is always 64 bits. That's really good. There's not that many systems out there right now that have a long in C as 64 bits. That gives you a pretty big range for your numbers. And the thing that you can appreciate and count on is the fact that they're always the same no matter what platform you go on. Float is 32-bit, double is 64-bit, and they use the IEEE floating point specifications. Here's a Java version of the average program that we had way back in Chapter 1. I'll call the name of the class average. Why not? Good idea. And here's my main function inside there. And I'll do what I did before. I'll declare a variable num1, which has a number, and num2, which has another. And what I want to do is print out the average. Well, all I have to do is sum them and divide by 2. Notice I'm dividing by 2.0. That works as it does in C. It makes a floating point quantity out of that, so it will keep the decimal points when it does the division. This program prints out the limits that you can have for your various numeric types, similar to the example we did in C. Notice that I'm printing out values that are defined in various classes like byte.minValue, short.maxValue. Well, those wrapper classes that I told you about, there's a capital B byte, which corresponds to the lowercase primitive type byte, and likewise for short and int and long and all of those. These wrapper types, among other purposes, have defined within them these maximums. And so the purpose of this program is just to print out the range of values that you can have, different types. So what this means is that the primitive type byte with a lowercase b can take on any value in the range of what capital B byte.minValue and maxValue print out. And the output is on the next screen. Well, these values are pretty reasonable, except notice that the long is quite big. Again, that's because it's a 64-bit integer quantity, and so you have quite a range there. The control structures in Java are identical to what you have in C. The loops are all the same, the for and the while and the do while, they're all there. Switch is there, it's all the same. There is a noticeable difference, though, and that is there is no goto. Instead of allowing you to have an arbitrary goto, there are some constrained versions of goto, and they are called the labeled break and the labeled continue, which I will illustrate on the next slide. Here's an example that will illustrate how to do the labeled break and continue, and at the same time it illustrates the for loop and the if statements, and that they're all the same as they are in C. So here's a class called label, which has a main program in it. And in this main program, I'm going to define a label, outer. And just like in C, a label is just a token followed by a colon. And now I'll go through my loops. I'll have a for loop. Now, here's one difference from C. You can define the loop control variable, or any variables you want to, inside of the header of that for loop. So I'm defining int I right there. So the scope of I will be that for loop. So I'll start off I at 0 and go up 2, but not including 4. And then I have a loop inside there, which declares a loop control variable j, which will also go from 0 through 3. And I'll be printing some things out. Basically, I'll just print out I and j, what they are. Notice in the print line statement, I can concatenate things with the plus sign. So any literal strings are printed literally, and any variables have their values converted to a string. And that's all concatenated into one big string, and that's what is printed out. And now I'm going to ask a couple of questions. If for some reason the sum of I and j is equal to 2, I'm going to cycle on the outer loop. And what that means is I'm going to skip out of the inner for loop and just repeat the outer loop. It'll increment I and do its test. And once the sum hits 4, I will break out of the outer loop. Not continue, but break. So you can see what happens here is that the continue does not just continue the current loop that you're inside. Now, if I just say continue, then it will, just like in C. But I can say continue with the label name, and it will continue the loop where the label is. That is, the label is right before that loop. And so this allows you to either continue on a nested loop or break out of it. And since you can label all of your loops, you have control over which level you want to go to. Therefore, you don't need a go-to. You just use a continue or a break with the appropriate label. Now let's trace through the output just to make sure. Of course, I and j start off at 0. And so I will print out 0, 0 for I and j. And the sum is not 2, the sum is not 4, so I will just continue on the inner loop. So j will be bumped up to 1. And I'll print those out. And then j will be bumped up to 2. And now at this point, the sum of I plus j is 2. So I'm not going to continue on the inner loop. I'm going to say continue outer. And so that's going to take me to the enclosing for loop, increment I, and now I is 1. And then I just fall through and start the inner loop again. J is 0. And I just continue the process like that. And then finally, I get to the point where I plus j equal to 4. And then the program halts. Objects are variables of a class type. And a class is just a type that you define yourself. It's like a struct in C. Except, of course, as you've seen, classes not only have data members, but they have methods or member functions as well. The distinguishing characteristic about objects in Java, though, is that all objects reside on the heap. There's no such thing as declaring one locally on the stack, or even globally. Of course, there's no global variables anyway. They always have to go on the heap, and the way you put something on the heap in Java is the same way you do in C++. You use the new operator that will create a new object on the heap, and it returns to you a handle, whereas C++ gives you a pointer, Java gives you a handle. Well, what does that mean? Well, they're practically the same thing, except for in Java you have no explicit pointer operations. So you can't dereference it. You don't have to, because it gets dereferenced automatically. You can't do any pointer arithmetic. That's not allowed in Java. You just don't have those things to get into trouble with. A handle can be thought of as an implicit pointer. You initialize an object in Java the same way you do in C++. You can use a constructor, which is a special method in the class. It has the same name as the class. And that is executed automatically when you declare an object of that class type. You don't have to worry about deleting the memory. I know that sounds kind of funny. We used new to put it on the heap, and the responsible programmer is always trying to make sure that he or she does not leave data on the heap. You always want to clean up after yourself. Well, you don't have to worry about that in Java because it does it for you. It uses garbage collection, which basically keeps track of objects and who's referring to them. And when objects are no longer being referred to, then they are marked for garbage collection, which means that at periodic points in the program, they will be destroyed and that memory will be reclaimed. In this example, I'm going to define an employee class like I did in the C chapters that we went through. That is, I defined an employee struct back then. Well, here we call it a class. And you'll notice that inside of the class definition, I put all of the data members and all of the member functions, but I have to put an access qualifier on each declaration. So my data, I want to have private, and that's what you commonly do when you define classes. You don't want the data to be public because you want to control it. Instead, you give functions that are public, and they are responsible for the behavior of the class. The first member function there is the employee constructor. It's a constructor because it's a function with the same name as the class. Constructors do not have a return type. This particular constructor takes 4 arguments, and so when you declare an employee object, you have to give it those 4 arguments, 3 strings, which will represent the last name, first name, and title, and then an integer which represents the age. And all this constructor will do, of course, is just hold that data, that is, assign it to the fields of the class. Now there's a special method called toString. If you define a toString method in a class, that method will be called whenever that object needs to be converted to a string. And in particular, what I'm talking about here is printing it out. The printLine method, which you've already seen, prints out strings, and it will automatically convert objects to strings. But when you define your own, well, you have to define that toString method. So I'm doing that here, and it will print out the data members of an employee enclosed by braces. The setLast method, of course, just takes a string argument and will replace the last field with that value, and so on for the other attributes, which you'll see on the next slide. Well, the first 3 methods on this slide are the set methods for first, title, and age. They don't do anything unusual. Let's go down to the main program. Now keep in mind that this whole time we are still in this class definition for employee. This entire file is just the definition of an employee class. But I'm going to also define a main function inside of here so that I can execute this after I've compiled the program. So what will this main program do? Well, it'll do pretty much what the example did in the C chapters. I will create an employee object. Notice how I do it. I use the new operator. Employee E equals new employee, and in parentheses I have the values that the constructor requires. The first thing I'll do is go ahead and just print out that object. And then I will exercise the methods of the class by changing the values of the fields. I realize at this point that, you're probably wondering, why do I bother having set last and set first and set title and set age and making the data private when I can just make the data public and achieve the same thing? Well, that's true in a simple example like this. But generally what you want to do in real programs is you actually do want to protect your data and only allow the operations that a user should have. And very often you won't have set functions like this. You'll just have the particular things you want the user to be able to do. Anyway, I'm going to go through and just make changes in all of these and print it out again. And each time I call printLine, it automatically calls the toString method of my class. That's just what printLine does. On the surface, it looks like arrays in Java are similar to C, but that really only is a coincidence. There's really a number of differences, major differences, and it makes arrays in Java more convenient than they are in C. First of all, range checking is enforced. When you declare an array in Java, the system remembers what its dimension is, and it does not allow you to index outside of that range. You'll get an exception. So that's good. The way that works is because arrays are objects in Java. They're not primitive types, and they're not in between. They are full-blown objects. Therefore, they have some standard behavior that all objects have. And for arrays, one of the things that you have available is a linked member. You can query an array at runtime to find out what its dimension is. And that's a good thing. Multidimensional arrays again, are similar to C, but they're different. They're similar in that the model of having an array of arrays is the same. Well, it's sort of the same. Actually, with a multidimensional array, you can allocate each dimension separately. It really makes it interesting. Not that you would want to do this very often, but see, you can define a two-dimensional array, but then the first row can have a different dimension than the second row. And again, the reason is because arrays are objects. They're dynamic. They're runtime types of things where you can do runtime operations on them. Now, before I let you go out of this slide, let me say that once you dimension an array, that is fixed. But what I'm saying is that you can actually dimension them at runtime and not just at compile time. First, let's just take a look at a one-dimensional array. This example behaves pretty much like you would expect a C program to. Notice the syntax difference, though. When I declare the array A1 as an array of integers, I say int brackets and then A1. Now, if you want to, you can do it the same way you do it in C. You can say int A1 brackets. I like to do it this way, though, because, again, A1 is an object. Well, what type of object is it? It's an integer array. And so it's nice to have those things together as the type token for that object. Well, this example doesn't do anything terribly exciting because it is, just like in C, it's implicitly dimensioning the array by the initializer list. So this will become an array of size 5, and it has the elements 10, 20, 30, 40, 50. But notice in the for loop, I use the length member so I know how many elements I have in that array. That's something that's automatically done by the system. It is kind of weird that length is a data member instead of a member function. Don't ask me why they did that. It is the strangest thing. I don't know anybody who thinks that that is intelligent behavior. That's just what they have done. Here's a two-dimensional array example. I'm defining A2 to be a two-dimensional array of integers, or better yet, if you recall the explanation of arrays from the C chapters, an array of arrays of ints. That's what A2 is. And so it follows the same model that you're used to, and you can even use the same initialization syntax with the nested braces. So this defines A2 to be the 3x2 array that has the first row 1 and 2, and the second row 3 and 4, and the third row 5 and 6. And I will use a nested loop to print these out, just like I would in C. But notice what I do for each dimension. I see what its length is. So for j, I say for int j equals 0, while j is less than a2.length. Well, what is a2.length? It's 3, right? Because a2 is an array of something. And how many somethings are there? There are 3. Those somethings turn out to be arrays of integers. But that's beside the point from this dimension's point of view. So, the outer loop processes the rows. And the inner loop will also make a query for each of those rows and ask, what is your length? And of course, in this case, the length is 2 for each row. But the thing that you're about to see in the next slide, and I'll just mention it now, is that those rows do not have to be the same size. They are in this case because I dimensioned them that way. That is, I initialized them that way in the initializer list when I defined A2. But you have the option of not initializing them and then dynamically declaring each row. And they can be of different lengths. This example shows everything you can do with arrays, more than you probably want to know. I'm going to define ultimately a three-dimensional array. But on my way to doing that, I'm going to use the arrays you've already seen. So for example, I have A1, which is a one-dimensional array with 5 ints. I have A2, which is a two-dimensional array with 3 rows. That is, each element itself is an array. And then finally, I'm going to declare A3 as an array of arrays of ints. That is, it's a three-dimensional array. And I'm going to declare it to have two elements. See how I did that? I say new int, and then I say 2 for the first dimension, and I leave the other 2 unspecified because I'm about to do those later. I'm trying to show you that you have a lot of dynamic control over how you size these arrays and what you put in them. So at the moment, all we know is that A3 has 2 elements, A3 sub 0 and A3 sub 1. But they haven't been initialized yet. They've just been allocated. So what I can do is I can put into A3 sub 0 the array A2. And it's an assignment. You cannot assign arrays in C, but you can in Java because they are objects. And so the first element of A3 is this two-dimensional array A2. Now I'll do something a little different for the second element of A3. I'm going to go through each row and allocate it and assign to it. So A3 sub 1, I'm going to just allocate space for a two-dimensional array which has 2 elements in it. So I'll try to keep in mind, what am I doing here? My second element of A3 is going to have 2 elements in it. Now my first element of A3 had 3 elements in it. And that's that 3 by 2 array. Well, okay, let's keep going. What is going to be my first element inside of A3 sub 1? Well, I will assign A1 to it. So A3 sub 1 sub 0 is A1. And what will my second element be? Oh, I think I'll just create a singleton array, an array of just 1 element. And I'll store that as the second element inside of this second element of A3. And now I need to put a value in there because it's uninitialized at the moment. And so I'll say A3 sub 1 sub 0 is 99. Now if you're confused about what this looks like, skip ahead to the next slide and you'll see the output. But what I'm doing here is I'm declaring a 3-dimensional array with 2 elements. Each element is itself a 2-dimensional array. Now the first one is pretty regular. It's that 3 by 2 array from the last slide. The second element, it's a 2-dimensional array, but it's not square or it's not rectangular. The first row is the numbers 10 through 50, and the second row is the single number 99. Now I can just go through with my normal pattern of printing out an array, and that is to query each dimension for its length and print things across in rows. So here I've printed the 2 elements of A3 out with a space in between them. The first element is the 3 by 2 array that has those numbers 1, 2, 3, 4, 5, 6. The second element is the 2-dimensional array that has the first row 10 through 50 and the second row 99. And again, it is not rectangular. Each dimension is dynamic. Well, there's a taste of Java. I realize it was a lot at once, but at least you get a feel for what it looks like and how it behaves. Everything in Java resides in a class. No such thing as freestanding functions. Everything belongs to a class. This really helps the organization of Java programs. There can be only one public class per file, and it has to be the same name as the source file, even down to the case. There's a good reason for that, but just don't have time to go into it. When you get into a more in-depth look at Java, you'll want to study what happens with packages to appreciate what's going on there. Everything in Java is either an object or a primitive, that is every data entity in Java. A primitive are the built-in types, and the thing that's nice about them is that they are portable, same size on every platform. Arrays are objects, and since they're objects, there's some overhead there, but you also get some nice behavior. You can query the length at runtime, and they're also a little different in that they don't have to be rectangular because each dimension is dynamic. Objects reside on the heap, so there's no question about where your objects are. That's just the way it is. You use the new operator to get them, and you don't have to worry about deleting them. They're cleaned up automatically. In this exercise, I'd like you to declare, I should say define, a stack class. Now, this is going to be similar to the example that you saw in the C chapters. And basically all you want to do is to have an array of ints inside of this stack class. And so you'll have to decide how big that will be. And the way you will do that is you will define a constructor that takes an integer argument, so that when you declare a stack, you pass it an integer which has that information. And then you will use the new operator to initialize that array of ints. And then just have it do the usual stuff, push, pop, top, and size like you've seen before, and also have a main method to test it. So you'll declare a stack with an initial value for its dimension, and then put some numbers on there and pop them off and make sure that it works. Well, now you've done it. You've finished and you're ready to really learn Java. Good luck.